Hi, everybody, and welcome to the NCDS DataBytes Lunchtime Webinar Series. Today's speaker is Gail Rosen, and Gail heads the Ecological and Evolutionary Signal Processing and Informatics Lab at Drexel University in Philadelphia, and recently spent a year as a visiting scholar at Weill Cornell Medicine, which is at Cornell University, improving taxonomic classification and analyzing the ambulance microbiome. Gail's main interests are in machine learning and evolution. She received a bachelor's, master's, and PhD from the Georgia Institute of Technology, and she's a recipient of an NSF Career Award, a Drexel Faculty Career Development Award, and a Lewis and Bessie Stein Fellowship Award. She serves on the editorial board of the BMC Microbiome Journal and as an associate editor of EuroSIP, Bioinformatics and Systems Biology. Today's talk is titled Continual Learning Systems for a Data-Intensive World. And as usual, the talk will last about 30 to 40 minutes, and after that we'll have time for Q&A. We ask you to type your general questions in the chat box when you think of them, and we'll hold them till the end of the talk and then read them back to Gail so she can answer your questions. So without further ado, thanks for joining us, and welcome, Gail. I'm going to hand it over to you.
Okay, great. I thank you very much for inviting me to this unique venue. It's a pleasure to talk with you all. So I'm at Drexel University, and I head up the Center for Biological Discovery from Big Data. And so what I'll be talking about today mostly is some of the algorithms, though, and you know, some of the challenges really. And how do we handle a lot of data that's constantly coming in? And thus I've titled the talk Continual Learning Systems for a Data-Intensive World. So there's two ways that you'll hear about continual learning systems, and number one is incremental learning, and the second one is online machine learning. So incremental learning is a more general term in which machine learning is used to continually extend a model in the computer, like a classifier or another type of model. And it's continually extending its knowledge to further train it. So while, on the other hand, online learning does the same thing, it tries to get a better predictor for each step. However, it assumes that all the data that it'll be examining is in sequential order, where this is not necessarily the case. So incremental learning is a little bit more of a looser constraint on online learning. Online learning assumes that you have to do it in real time. So where incremental learning, you can wait until you have enough data that you think you can make an inference. You can take data of different sizes, and we'll talk about that a little bit later. So just think of incremental learning as a little bit looser constraints of online learning. But all of these algorithms can be applied to different types of applications where we have just constant data coming in, and that could actually be on both sides. That could be for training the model, and that can also be the experimental data or data that's unlabeled. So I assume for training the model, you have labeled data most of the time, and you also have unlabeled data coming in. So you have both types of data, and actually later I'll propose that you can use both types of data to train the model. But for these types of applications, you can have social network analysis, categorizing and filtering news, tagging, filtering images, anything from the internet that's constantly being generated and that can be mined. And then finally, in my talk, I'll be showing a little bit how we're using this to disambiguate authors who may have the same names who may have the same name but are at different institutions or may change institutions. And so this is called the author disambiguation for scholarly citations, as well as I'll talk a little bit about how we propose to use this for genomics and in the future. Okay, so other applications could be the stock market. It could be some sort of anomaly change. So this could be for defense applications, or this almost looks like a graph that I was looking at when I was looking at airflow through vents in a building. If you want to see if there's all of a sudden a certain problem, and then security event monitoring and object tracking. So those are other examples where data is constantly streaming in. So this is kind of where how we can think about the model. So you have training examples constantly coming in. You have your learning requirements, and then you build your model, and then you have tests come in and you do predictions. However, the error between this model can actually be used with more input and more training examples to learn a better model. So what are the assumptions of such a system? Basically, data instances are continually arriving, and so you can also assume that they're constantly evolving and dynamic. So what may be a trend today on social media is not going to be a trend tomorrow. Stock markets follow different trends on the short term and on the long term. So we assume that this data is dynamic and constantly evolving. And so so we have to be able to train examples coming in at any point. Many of these systems work in finite memory, especially online systems. And we have to expect concept drift. So concept drift means that this model is dynamic, that the underlying model of today's data is not necessarily the underlying model of tomorrow's data. However, there might be a correlation. And so you have perhaps this drift of concepts that you could follow and be able to predict in the future. And then finally, you have to be ready to produce a classification at any time. So the arrival of continuous data, so how does this data arrive? Like I said before, you can have different setups where you can have instances where at each time step you assume that there'll be a new instance at each time, or you just set the time at whenever you get a new instance in. Then there's the opposite, where you can set a fixed time step and just take whatever data batch that you have at that particular time step. Other people also look at, well, I have a certain queue, and once I fill up that queue, I can take a set batch, and that way I'm analyzing the same size batch of data every time. And that's commonly used in the area of digital signal processing, is that you have a particular queue or window that you need to fill up, and you don't analyze the data until that's filled up. So there's what's called batch processing and instance processing. So with instance incremental learning, you want to update the model with new training examples as soon as they're available. And this is where you get into the online, and you assume that they're sequential, and thus you're processing them as soon as they're available. So many people think that this is the true incremental learning, whereas batch incremental, you can collect a group of training examples, then build a batch model with these examples and parameterize the model, collect more examples, update the old model's parameters with the new data, and repeat. So with batch incremental, you're not necessarily doing, quote, true incremental, where it's learning on the fly, but you can learn in batches, and we'll talk about the advantages and disadvantages of that. So with instance incremental, it's fast, and it's something that can be done, like I said, on the fly. However, the disadvantages are that you have a restricted choice of classifier. Not every classifier can be deployed in an online manner where you're updating the model with every instance. It might be too cumbersome. It might require retraining. So not every classifier can be used like that. Some classifiers, like the naive Bayes classifier, can actually use data that comes up and be integrated in, and you can actually not have to retrain the whole classifier. However, it may require massive, this requires massive numbers of instances to learn within instance incremental learning, and it may not adapt naturally to concept drift. So with batch incremental learning, the advantage is that you can use almost any classifier, and it automatically deals with concept drift because it's actually updating the model on every batch that it encounters. The disadvantages are that the most recent data is not part of the model. So, if you're a company, you may want to only wait every 3 months for web data, social network data to come in, and then update your model. Well, in that 3 months, you could be losing a lot of the new information that's out there. So it depends on your interval, and you won't have the most recent data integrated in your parameterization of the model. And so here you have to actually parameterize it, and that could be slow to learn as well. So I know that I'm introducing a lot of concepts here for people who are not in machine learning. So I thought I would back up a little bit, and so I will be talking a lot about supervised, unsupervised, and semi-supervised learning, especially unsupervised and semi-supervised. So for supervised learning, you have these dots that are colored, and you would then build a classifier off of those colored dots. And the classifier would probably draw what are called decision boundaries by illustrating these solid lines that would separate the red from the magenta from the blue. And then now when you bring in the black dots, those would be dots that we would like to classify. And so with this dot, we would say, okay, it's on the right side of this decision boundary, thus it must be the same class as the red dots. This black dot over here belongs with the magenta, it's on the same side as the magenta. So this is what we call supervised learning because we trained the classifier off of the labeled data that we had, and we knew all the labeled data for all the classes. We have 3 classes, and we had examples of each of them. However, with unsupervised learning, you may not know the clustering of the different data. So, so you may bring in just all this unlabeled data, and unsupervised learning algorithms can actually draw boundaries or cluster them and try to figure out the structure of the data from a totally unstructured input. So, and finally, really what really happens in the, in actuality is that you usually have a few examples of some of your classes, but then you may have things that you don't know about in your data. So you may have 1 example of the blue class, you may have 2 examples of the red class, and then you may have no examples of the magenta class. So it's a really interesting problem on how can we do semi-supervised learning, and it's in phases where you would basically, if you had the 1 example, you would first train what you have in the labeled data, which is the blue and the red classes. You would draw a solid line between them, and then on further updates, you would start to realize that, hey, as more data points come in, that this class up here is emerging as a class by itself, and then you could have a unsupervised algorithm basically cluster that, and I'm representing that by the dashed line. So just to give you an idea, right here I have unsupervised clustering. So basically I drew some points. They're all very similar, the boundaries are kind of blurred here. They're not well separated. And so an algorithm that uses a distribution, for example, a Gaussian distribution here, and tries to label the points based on that is dbScan. And so it's colored each of these points, and anything in red it's not certain about. So it hasn't really labeled those, but it's labeled the other points. So it can get a certain accuracy, but we can actually come up with better algorithms that draw decision boundaries between them, and I show an example of that here. So this is an example of clustering, but now you can imagine that instead of just having all these points right away, we're bringing in one data point at a time, and that's where incremental clustering comes in. Is we're bringing in one at a time, and we want to actually start to see how these clusters emerge and then separate them as we get more data. So just to also back up to give you some premise on some of the algorithms that we're looking at and building off of, k-means is one of the easiest and it's one of the first unsupervised clustering methods. It's simple but very useful. So if you have this unstructured data points unlabeled, all it needs as the input to its algorithm is how many clusters you think there are in your data. So you just can provide even a guess, but that's what it requires from you. And so you could try different guesses, but it bases everything off of that guess. So if you provide 3, you say, I think there are 3, you can either choose them randomly or perhaps you have a little bit prior knowledge that you could choose them with. But you would choose, say, 3 data points, and you call those the exemplars. So the algorithm goes and you then say, okay, the closest data points that are closer to this exemplar to any other exemplar get clustered with this exemplar. So this data point is closer to this one than it is to this one, so it gets clustered into this. These get clustered into this one. However, this one is closer to this than it is to this, so it gets clustered into here. So it then assigns the data points in that way, whichever one it's closest to, but then you'll realize that this exemplar is not really the centroid of this cluster. So the next step in the algorithm is then to say, okay, well, let's pick the point that is the most representative center for this cluster. So in this case, you can, this one is actually more centered to all the points. This one is more centered to all the points. And so on the next step, the exemplars then change for that cluster, and they get changed to these points. And then this one stays the same. This was the center, or the best representative for the center. So this exemplar stays the same on this iteration. And basically, on the next iteration, what you can see here is that this point now is closer to this exemplar than it was to this new exemplar. So it'll now get clustered over here. We can see it over here. So now we reassign the data points that are closest to the exemplars, and you can see that's an iterative process. Then we go back, we pick the best centers again, we reassign the data points, and it keeps iterating until it finally converges. So that's the gist of the k-means algorithm, and it's very powerful, and you get some clusters in the end. However, you have to have an idea of how many clusters there are. So, but some of the drawbacks is that it has a very long convergence time, and it could get stuck in a local minimum if you stop too early. So, basically, about I think a decade ago, Brendan Fry from University of Toronto tried to extend this concept into an algorithm called affinity propagation. And basically, the elevator speech for this algorithm is that all data points are simultaneously considered exemplars, but they exchange messages until a good set of exemplars gradually emerges. And you'll see they exchange messages about what are called responsibilities and availabilities, meaning if one's a better exemplar for another point, and if another point clusters with another point better. So it actually does this more in a matrix form rather than doing it one by one, which is what k-means does. So, but it's also a little bit more complicated of an algorithm than k-means. Remember, k-means, its only inputs were the number of clusters. But for the affinity propagation, you can see that we need two matrices. There's the pairwise similarities matrix, and then there's the exemplar where you place the exemplars. So for each similarity, the pairwise similarities, it represents how well K is an exemplar for point I. Whereas you may say, well, of course K is a really good exemplar for K. So what you do in these sockets in the matrix is you use that as a prior preference for how much should that K be chosen as an exemplar from the outset, as an initial condition. So you could get this prior preference from some information you have, or you could even guess, or maybe use k-means to initialize something that you figured out from another algorithm to initialize these values. And then, and the same thing with what you actually set the exemplars, whether that's an exemplar for that point or not. So in the end, you want to optimize the objective function and of affinity propagation. And you note that the number of clusters emerges automatically from the optimization of this algorithm of the similarity matrix times the exemplar matrix. I just hear, is everybody there?
Did I say something? Yeah, we're here. Sorry, we're muted, but we can hear you well.
Okay, I just wanted to make sure because it's so silent that I was like, am I just talking? Okay.
yeah, we're here.
Okay, great. Yeah, so you want to maximize this affinity propagation objective function between the exemplar points and the similarities and the prior preferences. And so note here that you don't really need to know the number of clusters and that they'll emerge, but they'll be initialized by this prior preferences. That they could go to another value. So even if you pick, you think that there are 3, but there are really 4 or 5, it may go to 4 or 5. If you initialize with, you think there are 3, you put that in the prior preferences, however, there are 100, it may not do as well for such a jump, but it could emerge if the guess is pretty close. Okay, so I'm not going to get too much into the algorithm because I think the audience is pretty broad, but basically just to get to the nuts and bolts on how this is working is you're optimizing this function, this cost function, and so you introduce terms that have a penalty for having a cluster without an exemplar, and then you also have a term that has a penalty for a point being assigned to more than one cluster. So, of course, you don't want a point to be assigned to more than one cluster. That's definitely something that can't really happen with k-means. And then you don't want a cluster without an exemplar. So basically, you have these two penalties that you're optimizing for, and then these points the matrices pass information back and forth, and I skip a bunch of steps, and what happens is that you can restructure this term into what are called responsibilities and availabilities. And what it does is points can actually influence other points and say that you may have a candidate exemplar for this data point 1, and that it may start to feel from some of the weights that there's a competing candidate from another a competing candidate exemplar from another point. And then you may also have a data point and that there's a candidate exemplar and that it's getting more support from this one, and therefore it says, you know, I think I'm a candidate for you, and then this data point can go back here and say how much that it thinks it needs that candidate. So you have this competing responsibilities and availabilities. And they can be thought of as exchanging messages between them, and this has type theory with belief propagation and any sort of algorithm where you have message passing. So we kind of took this algorithm because, right, again, it only works for set data sets, and we got it to work for incremental learning. I can't go too much into the algorithms that we have developed because we're working with some companies and filing provisional patents, but we were able to get it to work for an incremental case. And you can see here that we start out with 3 clusters. And so when we start out with some of the points, they're forming their own individual clusters here in the red, and then 2 clusters in the black. And as we go along, they're going to start to join together as we get more and more data points from these 3 clusters. Then at the end, we're going to introduce a whole new cluster, and it'll start to form its own cluster right away. And then I have the running accuracy rate up here. So you can see that already only this one black point is getting confused. These points, of course, are halfway in between the 2 clusters, so they're getting confused. But these are now all joining together, and the algorithm is pretty well converging on a set of clusters. And then soon we're going to have the green one here, and then its initial points get some confused, but it easily starts to join together. Okay, so that's an example of, you know, as we get more data, how can we fit it in? And so we did a simulation there with affinity propagation. So another way is the semi-supervised learning. So what happens now if you already know about 3 of the clusters and we have our decision boundaries, and then we're going to add data from the 3 clusters that we do know plus an extra class. And we're working on algorithms to see, can we determine, you know, all of a sudden we've determined, hey, that's a new class, and then we can label it on the next step. So we're applying this to several different problems. So one problem is the scholarly citation data, and there are a lot of caveats with this where we're mainly examining the problem of, you know, you have 4 different authors and they all have the same name. However, we also have issues where the name might be backwards. They also might have their first name abbreviated. So Imran could also be a Mustafa, so we have to now distinguish, you know, which one of these Muhammads are different from Mustafa. So so the different name ambiguation types, we can have the database, and we have these different authors, and they can each have their own citations that we want to combine and figure out which one is each of the authors. So here's an example. We show that we're applying it to the citation data as the citations come in. We have 160 papers that will be coming in. They belong to 4 authors, so we know the ground truth on this data. And then these are the types of observations and features that we're observing about it. we know the address, their address, the authors of the paper, the institution of each of the authors, the language of the paper, the subject of the paper, but not only things about the paper, but we also know papers that have cited that paper, their languages, their source, their subject, etc. So this is information that you can, even find on Thomson Reuters in their citation database. So we took this information and we look at, we're going to be visualizing here the pairwise similarity matrix between the documents. So if it has really high similarity, we're going to mark it with a yellow, low similarity with blue, and anything in between here. And then here we're going to actually show the predicted author, pairwise authorships. So if it's the same author, it's going to get yellow. If it's the ground truth is definitely a different author. So these two ends indicate the ground truth. And then if there's a different, if it should have been the same author, but it was predicted as something different, you're going to get this green. And if it's a different author but predicted, so a misclassification will kind of be in this green area here. So at the beginning, we can see that there are a lot of, these are the document number. Remember, we're bringing in 160, so we have a lot of misclassifications here at the beginning. And they don't have, surprisingly, they don't have that much similarity with them, but we kind of weighted their similarity not to get something too high because otherwise documents get confused. So we had to optimize this similarity metric, and we weighted it on purpose and found the optimal weighting to get these pairwise authorships. So, and down here we keep a running, we get, another thing is we get 100% precision. So what's happening, what this indicates, and that recall is going down, is that we're generating a lot of clusters, but each of the clusters has the same author. So therefore, it's 100% precision, and as we generate more and more clusters, our recall is very much going down. But what you'll see when we get the next author, so now that we get papers from the next author, is that precision goes down a little bit, recall goes up a bit, but our precision goes right back up, and we're starting to at least be able to distinguish between the authors. However, we still have too many clusters of citations between the authors. So really, this is in the end, we're showing here that this is a very difficult problem, that these methods tend to generate too many clusters given this citation data. And we can generate a lot of clusters, and that afterward we need to merge the clusters to make sure that they all belong to one author, and that would be the next step in classifying these. But here we can see, in general we get the predictions, but there are some misclassifications. So in the future, what we hope to do is apply this to the field of metagenomics, and it's very important for metagenomics since the cost of sequencing is outpacing Moore's law. The amount of DNA being sequenced is just exploding, and computational power cannot keep up. So can we come up with really continual learning systems to keep up with all this data that's coming in without having a slowdown of computation? And so the reason why they're really exploding here is that we have microbial communities are found everywhere, in the soil, in the ocean, in our gut, on our skin. They are even thought, some of the serotonin release is thought to influence the brain and other types of secretions from our microbes. And also, it's thought to affect the health in the indoor environment. So a lot of biologists are taking a lot of samples, and we're sequencing, gigs and gigs of DNA from each of these samples. So right now, the way that this classification is being done is by you have a reference database where you know a certain set of microbes. So in this example, it would be 5, and you classify them and you get some results. But however, when you take in a new sample, after there's an update to your database, so you may update your database and then you bring in some more studies, and this sample now gets classified against this new database. And that's what most people do, and therefore their results are incomparable to these results because maybe these samples had these extra 4 organisms that we didn't know about back then that were not labeled. So they are not labeled in these samples, and how could we compare between these studies when they were never labeled in these samples, but they were labeled over here? So there's a lot of inconsistency in metagenomics data sets, and what I propose is that we actually take a semi-supervised learner that can actually integrate not only labeled data but unlabeled data into the model. So what would happen is we would have this labeled reference database coming into the model. We would also put our samples, and that would help the model, as well as we classify them at the same time, and we get some analysis on the output. However, when we have new genomes to put into the database, as well as new samples, it gets integrated with the old database. The entire database gets integrated. That database then updates the results for the old examples as well as the new example, and we will have all the samples, consistent, as well as we'll have a learner that's leveraged by the new data, the labeled data, and the unlabeled data. So the way that to delve into the semi-supervised learner and how it works a little bit better is that you would have these bold dots, which are the labeled data, and you would be able to learn them. And I'm representing like the model with a centroid that I mark as an X. So we would be able to learn some parameters. So the X represents some parameters that we would learn about these different classes. And then we'd be able to draw decision boundaries based on these parameters. And on the next step, we would bring in unlabeled data, which I have in the lighter colored dots that correspond. So if it's blue, I assume that it's an unlabeled dot that may belong to the blue class. These would belong to the orange class, etc. However, they're unlabeled. But what we could do to actually improve our model, even though we don't know exactly that even though these are unlabeled, is that we could classify them and say, they really belong the closest to the red label. So therefore, they're red and they're really close to our old labels, and they provide some information that we didn't have before. So we could actually use this unlabeled data now and say, we are confident that these are part of the red class. We will incorporate them in our model. We'll leave out the stuff we're not confident about. For example, is this cluster over here, does it really belong to this red dot, or was this red dot mislabeled to begin with, and we're uncertain? So we leave that data out, and we build a new model based on our confident data. On the next step might be that we bring in a new genome. That would be the purple dots, and we could then say, hey, we think we found a new genome. That's a new class. Let's look back at our old data. Oh, we can now relabel these data sets with this new class. We know that these are now purple. Even though they were red dots to begin with, we can relabel that old data set. And that's something that we could do in a continual learning classifier over and over. And that's what I've been proposing for our future work. So I hope that this gave you a lot of fodder to think about with continual learning systems and how you could use labeled and unlabeled data and instances and be able to learn on the fly and update and parameterize your models. But I really think Zhenxiao Zhao for the work. He did a lot of, he did all the simulations and for this presentation, and he's been working on a lot of the theory. We're just now starting to implement it in for real systems, and this is our future project for this year. So also I'd like to thank Steve Wozniak, and hopefully we can talk about some of his work sometime. But I really appreciate you inviting me to this seminar, and that's what I have for now. Thank you.
Gail, thank you, excuse me, so much for your talk. And at this time, I'd like to invite anyone from the audience to give us some questions. We've got a lot of people online here, but they're all very quiet. Anything? I don't see any questions, but I invite anyone that has questions to contact either me directly and I can get you connected with Gail if you have anything. And I have comments saying thank you, this was fascinating, and a few like that. Also, this will be put onto the NCDS website if anyone wants to go back and refresh their memory on what the talk was about. Sometimes people need to think a little before expressing, figuring out what they want to ask you. So it usually takes about a week for those to get put up. For everyone in the audience, remember this is a monthly lunchtime webinar series, and we're usually holding them on the first Wednesday of the month, which means that our next session will be Wednesday, March 1, and also at noon. Our speaker then will be Monica Horvath, who is Director of Health Intelligence at ThoughtWave Technologies, and she will be discussing tactics to grow analytic thinking that every health organization can use. So we hope you can join us on March 1. We thank you for joining us on February 1 as well. And if there's nothing else, then I want to again say thank you, Gail, and everybody have a great day and a great month of February.
All right. Thank you.
Thanks, Gail.